Okay, so now let S be the set that we already defined in the lemma that we used to prove the Stein theorem. Is the complex numbers set, uh, which has the real part between 0 and 1. So suppose that for each set we have a linear operator tz defined on the space of simple functions in L1 x. Okay, so the it goes into measurable functions on y. Okay, so let's put my measurable functions in y in such a way that if we make t set of f, okay, and then g, this is integrable on y, okay, and provided that this is well, a function in a simple function in L1, and g is a simple function in L1 y. Okay, so let's define the family of operators um, tz, z is in S. The family is called admissible if the mapping Z onto the integral in y of tz f g dp is analytic in the interior of S, okay, and there exists a constant a is less than pi, such that e to the minus a absolute value y log absolute value the integral y tz f g dp, okay, absolute value, okay, is uniformly bounded, okay, is bounded above in the strip S, okay. Recall the strip S are the complex numbers which has the real part between 0 and 1. So, theorem by Stein, okay, an interpolation theorem. Suppose that the family Tz is an admissible family of linear operators that satisfies that norm of T. Now the complex number is Iy, okay, of f, norm q naught is less than equal than m naught y, f p naught, and now t1 plus Iy, recall the boundary of S in this part, norm q1 to be less than equal than m1y, norm of f p1, okay, with y a real number, okay. This is for all simple functions, okay, f in L1x, this is an x, and where, okay, 1 is less than equal than pj, qj less than equal than infinity, okay, and mjy with j equal to 0, 1 are independent of f and satisfies on the supremum minus infinity y infinity e minus b absolute value y log mj y is less than infinity for some b less than pi, okay, okay. Okay, so we have Tz, an admissible family of linear operators that satisfies that Tiy is less than this bound, and T in 1 plus Iy has this bound, okay, where we establish where Pj and Qj lives, okay, and we, we establish that um, the bounds satisfy the supremum of E, okay, is less than infinity. So these are all the conditions. Then what we are going to have. So then, if t between 0 and 1 exists a constant empty, okay, such that the norm t uh, t of now is t the operator, okay, t, this t of f, norm qt is less than equal than this mt multiplied by f, okay, pt, and this is for all f simple functions that provide that, okay, and we have this relationship 1 over pt 1 minus t, okay, um, you will recognize this relationship uh, in Risterin and many others. We've been using this kind of relationships for um, the numbers that are in the norms and in the spaces. Okay, so I'm not going to prove it, but it's another important interpolation theorem.